So, hello everyone. It's a great pleasure to have here Professor Wendy Freedman today. Thanks a lot to Wendy for accepting our invitation. Professor Wendy Freedman is one of the 9 named university professors appointed by the President of the University of Chicago. Wendy received her doctorate in astronomy and astrophysics from the University of Toronto. Then she received a Carnegie Fellowship at Carnegie Observatories in Pasadena, in California. And then she joined there the permanent staff. And finally, she was appointed as the Crawford Greenwald Director. Wendy served as the founding chair of the board of directors for the Giant Magellan Telescope. He's an elected member of the National Academy of Sciences, the American Academy of Arts and Sciences, the American Philosophical Society, an elected fellow of the American Association for the Advancement of Science, the American Philosophical Society, Physical Society, and the Royal Society, and a legacy fellow of the American Astronomical Society. Wen is one of the 3 co-recipients of the 2009 Gruber Cosmology Prize, and has also been awarded the Dan Yeneman Prize for Astrophysics by the American Institute of Physics and American Astronomical Society. Her main research interests are in observational cosmology. Wendy was a principal investigator for a team of 30 astronomers who carry out the Hubble Key project to measure the current expansion rate of the universe. Presently, research interests are directed at increasing the accuracy of measurement of the expansion rate and testing whether there is new fundamental universe physics. Wendy is currently PI of the Chicago Carnegie Hubble program. This program uses the Hubble and James Webb Space Telescope to measure the Hubble constant using Cepheids, TRGB, JAGB stars. She has been instrumental in developing the TRGB and JAGB methods, as well as developing means for decreasing their systematics in the Cepheids distance scale. Today, she will present the Hubble tension, new result from JWST. Wendy, please, you can start when you're ready.
Well, thank you for the invitation. It really is a pleasure today to tell you about some new results that we have from the James Webb Space Telescope and what they can tell us about measuring distances to nearby galaxies. And what I'll tell you, this is a status report. I am not going to give you a solution to the Hubble tension. I think the question is open, and the current data allow for both the standard model to survive and also for the possibility of a Hubble tension. And I think it's very clear that James Webb Space Telescope, and this really is the focus of this talk, is this powerful new facility that has almost 4 times the resolution of the Hubble Space Telescope and nearly 10 times its sensitivity, and can help us address some of the potential remaining systematics in the extragalactic distance scale, and therefore the determination of the Hubble constant. So our group, so I don't seem to be able to advance here. Okay. Our group, the Chicago Carnegie Hubble program, proposed in cycle 1 of JWST to measure the distances to nearby galaxies, all of which have had type 1a supernovae in them and had distances measured by Cepheids, primarily by the SHOES group and also by the Key Project group in some cases. And the emphasis is on measuring accurate distances, trying to overcome the systematics that we know have been a challenge in the extragalactic distance scale. Now, we know that galaxies are all at the same distance, or at least a single galaxy is at a single distance. I think that's something we can all agree on. And it's important to have independent methods with high precision, each of the methods, so that we can compare them and ultimately understand what might be systematic effects in one or all of the methods. And very likely, they each have their own systematics. We need to quantitatively ascertain at what level those systematics are playing a role. And the way to do that is to have independent measurements to the same objects. So we're using the Cepheids, the sort of gold standard that have been in use since Hubble for a century, the tip of the red giant branch, and a new method, relatively new method, the J-region asymptotic giant branch method, or JGB. And I'll have more to say about those. Now, historically, of course, we're all familiar with the fact, and I know this is an audience that I don't need to explain the Hubble tension to, well familiar with the Hubble tension. But let's step back for a moment and look at the 1960s, 70s, 80s, 90s, when we were measuring Hubble constants. Measurements were ranging from 50 to 100. There was this well-known factor of 2 debate But you can also see that, I don't know if you can see my cursor, but there were values of the Hubble constant in the literature that were between those two values. And ultimately, this was resolved with the Hubble Key Project, the launch of the Hubble Space Telescope and our program to measure accurate distances to nearby galaxies. Now, today we're discussing differences between 67 and 73 or so kilometers per second per megaparsec. It's an enormous increase in the accuracy and the precision in the distances that we can now measure to nearby galaxies and stepping out into the Hubble expansion. But what we're now asking is, not only is this difference between 67 and 73 significant, but are the uncertainties contained within essentially the width of these lines, so that this is a 5 sigma tension and signaling potentially new physics. And that's what we're all aiming to try and ascertain. Now, historically, and I think today, the distinction we need to make is between precision and accuracy. And I think our precision and accuracy have both increased. But of course, we can make measurements many times at very high precision. But if we're missing the target, then we're not measuring our accurate value of the Hubble constant. So we need to ensure, and at each level, as we've brought down the systematics, and the name of measuring the Hubble constant really has been a search for and bringing down the systematics. At each level, as the technology has improved, and the reason that the precision and accuracy both have improved is because of advances in technology, in charge-coupled devices that replaced photographic plates, the wavelength dependence now being able to go into the infrared, near infrared, to correct for systematic effects like dust that it wasn't possible to do before the launch of Hubble, or at least until CCDs. And we began that work on the ground. And so just as an example, one of the reasons why there was this systematic, long-standing disagreement about the Hubble constant was the inability to make accurate corrections for the presence of dust. And recall that Cepheids are young stars. They are found in regions where there's ongoing star formation, there's dust, and they're in regions of high surface brightness so that they can be crowded or blended with other stars. And that makes the photometry that much more challenging. So we began in the 1980s to obtain CCD photometry for the first time of Cepheids in nearby galaxies. So this is the galaxy M33. And when we measured the distance modulus, the apparent distance modulus, as a function of the inverse wavelength of the observations, now extending out into the I band, in this case at about 8,800 angstroms, you can see that the apparent distance modulus decreases as you go to longer and longer wavelengths. And what that allowed us to do for the first time was actually make a correction for the dust obscuration that had not been possible before. And of course, the CCDs with 99% or so quantum efficiency made the photographic photometry obsolete, and it was possible to make much more accurate measurements. And ultimately, with the launch of Hubble, initially, we were only able to make observations at V and I for our target galaxies with Hubble. There was no infrared camera when it was first launched, but eventually the NICMOS camera was put onto HST, and this is our early days of infrared photometry with Hubble in JHK. That allowed us, again, to check the reddenings that we had measured for the Hubble Key Project at V and I, and those agreed very well. And then with the advent of Spitzer and going into the mid-infrared, we were able to make multi-wavelength observations, and again, correct for the presence of dust. So these are the kinds of things that really have improved as our technology and capability have strengthened with time. Okay, so these are just showing the HST Key Project final results combined, and the again, name of the game for the Key Project was to go after potential systematics. And our philosophy then, and our philosophy for the Chicago Carnegie Hubble program, is not to put all our eggs in one basket. That is, if there are systematic effects in a given method, and there will be, we don't know at what level, and the only way we can quantitatively assess at what level is to make measurements with completely independent methods, and that way constrain, get a more robust estimate of the overall systematics. And so we used 5 methods shown here. Most of the work done since the Key project has extended the supernova distance scale, the type 1As, largely because they're very bright. They can be observed to very large distances, and the scatter in the Hubble diagram from the type 1As is quite small. We also, not well known, is well known for the Key project, use the tip of the red giant branch distances, and also in cases where they're available in nearby galaxies, our Lyrae distances, to test the Cepheids. So at each level, we had independent checks of the distances, and we measured this value of 72. With a 10% uncertainty, that was our goal, and the project was designed so that the statistical uncertainties in each of these methods, the numbers of objects that we observed, would allow for 5% statistical uncertainty, and therefore to have an overall estimate of 10% in the in combined systematic and statistical uncertainties. And I think that really has stayed pretty steady with time. If we look now at the values of the Hubble constant since the Key project, and the values shown in red here are those that are calibrated by Cepheids, largely extending out with the type 1A supernovae. And most of this work, this heroic work, huge amount of work has been done by the SHOES team to use Hubble to find Cepheids in galaxies that also have hosted type 1A supernovae. This value here, the Carnegie Hubble program at that time, is when we used the Spitzer mid-infrared telescope to extend the Key project calibration. So what you can see, again, the value has remained constant, 72 to 74 based on Cepheids. But what has really improved is the uncertainty in those values, and now the measurements from the SHOES team have estimated an uncertainty at the 1% level. And I think the other interesting point, and certainly a motivation still, I think, for us all to understand whether there are remaining systematics, is to notice that in the overall published distances, and again, there's not a bimodal distribution. There are values of the Hubble constant that continue to be published that really do fill in the range, say from 67 to 73. But the Cepheids do tend to lie at the high end of the distribution. Now, that may turn out to be correct in the end, and it may also potentially be signaling that there's some sort of systematic. So I should mention these data. It was a database originally that was maintained by John Huckra, and since John's untimely death many years ago now, it maintained and updated by Ian Steer. Now, here are the recent papers that our group have posted, one on our status report on our JWST and Hubble constant analysis, and also a paper that details the JAGB distances led by Abby Lee, graduate student at the University of Chicago. And we have papers upcoming on the TRGB distances by Taylor Hoyt, who's now postdoc at Lawrence Berkeley Lab, and Kayla Owens, who's a graduate student again at University of Chicago. And we have papers in preparation on the photometry and further Cepheid analysis by In-Sung Zhang and Barry Medor. I just wanted to highlight too the work that has gone on prior to this work with JWST, and in developing these methods and in improving the accuracy with which we can measure the distances to nearby galaxies. And I think going back to some early work, at the University of Toronto, a group including Barry Medor, who were the first to actually use infrared photometry to show that the dispersion in the period luminosity relation for Cepheids in the near infrared is considerably decreased compared to the optical. That's a result of the decreased sensitivity to temperature of the surface brightness at these infrared wavelengths. And then, as I mentioned, with the advent of CCD detectors, we're able to get multi-object photometry and correct for dust for the first time. That had not been done in the extragalactic distance scale, and that became the basis for what we did in the Key project, and it's the basis of what everyone now uses for measuring Cepheid distances, multi-wavelength photometry. We did the first empirical tests for metallicity when CCDs became available, and used the metallicities, oxygen to hydrogen abundances of H2 regions as a proxy for Cepheid metallicity, because we can't measure the Cepheid metallicities directly for galaxies that are at the distances that we're measuring. So again, we did that for the key project, and that's what people again use today to allow for differences in luminosities of Cepheids as a result of differences in chemical composition. So much of that was detailed in a review paper that Barry and I wrote in the early 1990s. And then we went on again to do infrared photometry of a large sample of stars in the Magellanic Cloud, and showed just how well, if you have good high signal noise data, you can do in the infrared. I mentioned the Spitzer data that we recalibrated the key project distance to the Magellanic Clouds, and the key project to all based on Cepheids. We turn to the tip of the red giant branch, going back to a paper that we wrote in 1991. These are members of the Chicago Carnegie Hubble program. And at the time, postdoc Myung-Gyun Lee and Mary and I looked at, again, new CCD photometry we were able to get for the first time for galaxies nearby, and to show that the tip of the red giant branch was quantitatively a really accurate distance indicator and had a lot of potential. And as I said, we did use it to test the key project Cepheid distances at that time at a 10% level. And we have continued to develop the method, and culminating in then a Hubble Space Telescope project where we applied the method to galaxies that were host to type 1a supernovae, which we did in 2019. Followed up in 2021. And most recently, we developed this new method, which we've called the JAGB method. And that is making use of a type of star I'll describe more in a moment. It's an intermediate age star. It's a different population than the TRGB or the Cepheids. And based on ground-based data, first, Barry and I compared the distances that we measured using this new distance indicator, and it agreed extremely well with the TRGB distances, and that motivated us to our proposal for cycle 1 to include that as a method that we could use independently of the TRGB and the Cepheid. So many decades of work that have allowed us to get to this point, improving the distances and improving them still, and where we can go with JWST. And we are just starting with JWST. Whoops, I've gone backwards. Okay, so what are the challenges in measuring an accurate local value of the Hubble constant? And immediately, if you look at the Hubble data, and I'm not saying anything to say anything negative about Hubble. Hubble has been a fantastic instrument for finding Cepheids in nearby galaxies, and it allowed us to get above the atmosphere for the first time, allowed us to deal with crowding effects that had been a problem on the ground, earlier observations. But now pushing Hubble to really its limits, and when we're trying to measure distances to galaxies that have type 1a supernovae, the supernovae are rare. They happen only, say every 1 to 2 years in galaxies that are close enough to access with Hubble, for which we can measure Cepheids or tip of the red giant branch or JGB distances. So as I mentioned, the amplitudes of Cepheids are largest at optical wavelengths. And so finding the Cepheids is done in the optical. That's what we showed with ground-based data and then with HST, and then the follow-up in the infrared to get to as red a band as possible where the effects of crowding, of reddening are least. What we didn't anticipate, however, was that the crowding effects in the infrared would be larger as you go to longer and longer wavelengths. And that's because the red giant branch stars and the asymptotic giant branch stars, even brighter AGB stars, now are crowding your Cepheids. And they're too faint when you're observing at optical wavelengths, but they come booming up, as we can see, as you go to the near infrared wavelengths. So the red circle here is denoting where a Cepheid has been discovered by the Shoes group at optical wavelengths, and that's its position where the Cepheid lies at H-band at 1.6 microns. Most of the distance determination comes from the H-band. So this is a galaxy at 20 megaparsecs, relatively nearby in terms of the sample. And you can see immediately the improvement that comes when you go to JWST. So this is an image, this previous image is of HST at 1.6 microns, and this is JWST at 1.15 microns. So getting accurate photometry is the immediate advantage with JWST. Another example, so this is now, they're matched, the two frames from HST and JWST, in a way that the pixel size is matched given the drizzled images. Again, you can see HST, there's a lot of bright stuff around the Cepheid. The signal to noise is not superb when you're trying to measure the brightness of the Cepheid itself against the background in which the Cepheid resides. And here's what happens when you get JWST data. So, just at a glance, you can see this is going to be an enormous improvement. Now, just to emphasize that 20 megaparsecs, the distance of this galaxy, the Cepheids are already crowded by stars that are contained within an area that's 8 times larger than the area of in the galaxy NGC 4258, the comparable area. And so this is on the detector. So the detector, of course, a fixed size, but your galaxy, as you're observing farther and farther away, you're getting more and more of your galaxy for a fixed resolution element. And if you go to 40 megaparsecs, and so 60% of the sample is at a distance greater than 20 megaparsecs, the current SHU sample, and 25% is at a distance greater than 40 megaparsecs. So you already then have an area that's 33 times larger than your calibrator, and lower signal to noise. So I should point out that, again, the signal to noise of the JWST data is much higher. And just other examples here, and you can see, so the optical data are shown here, and my bar here is blocking. Yeah, so this is the 555W, so it's equivalent to the V band at about 5,500 angstroms, and then the I band here at about 8,000 angstroms, or 0.8 microns. This is the HST data again, the F160, 1.6 microns from HST, and here you can see the JWST 1.15 micron data. Okay, so the results that I'll show you today, the tip of the red giant branch data are based on the JWST data alone. So the JWST filters allow us to measure those distances, but we still need to correct the Cepheid distances for dust and also for metallicity or chemical composition. And so we still need to rely on the optical data from Hubble. So the optical data, as we saw, has better resolution than the infrared, but it still has difficulties with challenges with crowding and overlapping of images, I would say. And I think, and so we still, it's a hybrid of both. And I also should mention that we've reanalyzed the data in the archive. That's the first time this has been done. Other people have analyzed the SHU's data, but they start from the already reduced data. We went back to the raw images and went from there. And I should say that all of these data will become available on GitHub once those papers have been completed. So I think probably most people in this audience are familiar with JWST, but just to remind you, is a telescope that's operating at the Lagrangian, second Lagrangian point. It's an Earth trailing orbit. It's about 1.6 million kilometers from the Earth. And the primary mirror has a diameter of 6.5 meters, so compared to Hubble's of 2.5 meters. And this telescope has been optimized for the infrared. That is, there are gold-coated beryllium mirrors, which are cooled and allow you to have sensitivity in the infrared far greater than available with Hubble. And so our program, once again, is to measure the distances using these 3 independent methods applied to the same supernova 1A hosts. And I should say that we started off, and the intention was to do everything completely blind, so that the different parts of our group that were working on these different distance indicators knew nothing about the analysis of the other methods. And the way we did that was to apply random numbers to each of the photometry catalogs, and so that all the analysis was done with arbitrary 0 points and no knowledge of the Hubble constant. And that we were able to successfully carry all the way through for the JAGB analysis. And so I should say we measured period luminosity relations for the Cepheids, the luminosity functions for the tip of the red giant branch, and the JAGB method, and did artificial star tests, which I'll describe more in a moment. Not all of the artificial star tests had been completed when we did our what we had intended to be our final unblinding, but for various reasons. But that's just the way things went, and we discovered an error in the pipeline for the Cepheid photometry subsequent to the unblinding. It was just an additive offset, but nonetheless it happened post-blinding. And the statistics, the uncertainties for the 4 of the TRGB galaxies were such that allowing for a larger spatial cut provided more stars for measurement of the TRGB. The differences were well within 1 sigma, but they improved the measurements. But we don't consider that to be completely blind. It happened post-blinding. Here are our fields, and it doesn't show up well on the screen. I don't know if people could see, but the red outlines here are for NIRCam, the camera, near-infrared camera on JWST. And there are 2 cameras, and we pointed one of them at the disk of the galaxies so that we could get the Cepheids that had previously been discovered, and also out into the halo where we could measure the tip of the red giant branch, and the outer disk where the JAGB intermediate age stars can be measured. Now, the TRGB and JAGB stars, of course, do occur in the disks, but the challenge of the disk is that we have to correct for reddening, and the effects of crowding and blending are enormously greater in the disk where there's been lots of star formation. And out in the halo, these stars aren't crowded and there is no dust. So it's a big advantage of the TRGB method. So just to show you, this is the HR diagram, or the color magnitude diagram, observational equivalent for JWST data. This is the 1.15 micron band, and a color here. We used 2 different filters. We went away from this 4.4 micron band eventually, just because we wanted to get higher resolution. But this was one of the nearer galaxies in our sample, and you can see where the Cepheids lie. They're the brightest of the distance indicators that we're looking at. Here's where these JAGB stars lie, and here's where the tip of the red giant branch is. And we can do this with the same calibration. So these are all done with NIRCam, all the same calibration. We are using NGC 4258, which is the galaxy that has masers, water masers that are orbiting its central black hole, for which you can get a geometric distance by measuring both the transverse and the radial components, a geometric distance to the galaxy. So just to emphasize, these have completely different systematics. These are completely different populations of stars, but and different evolutionary stages, but we have the advantage of using same detectors, filters, point spread functions, and absolute calibration, so that when we compare the distances, we're not introducing other differences that might arise with different telescopes, filters, calibrations, etc. So tip of the red giant branch, not as well known again as the Cepheid PL relation, but these are low mass stars that have a degenerate helium core surrounded by a hydrogen burning shell. And what governs the luminosity of these stars is actually well understood nuclear physics. Of the 3 methods, this is the one that has the best understanding from a physical standpoint. Now, the star continues to burn hydrogen in the shell, and it's depositing more helium then, as it's fusing hydrogen to helium in the shell, onto the core. But the core can't expand because it's a degenerate core, and the temperature continues to rise. And when it reaches a temperature of 100 million degrees, that's the point at which you can start nuclear burning of helium, the so-called triple alpha process. And because, again, it can't expand, you get a thermonuclear runaway. And this happens very rapidly. The star then ends up burning helium then in its core and settles onto the horizontal branch, much fainter magnitude, about 4 magnitudes fainter. So the again, just to emphasize, because of this degeneracy, this ignition of the helium happens at an almost constant core mass, and therefore a predictable luminosity. And the observational consequence of that is when we look again now at an HR diagram or observational color magnitude diagram, you see the red giant branch here. The star ascends the red giant branch, and when it gets to this so-called core helium flash that has been modeled now for decades, well understood theoretically, then you don't get the red giants continuing to evolve to higher luminosities, but they fall down onto the horizontal branch then. So here in gray, showing the luminosity function for this population. And you can see even by eye that there is a well-defined position where the core helium flash occurs. I mentioned here, these are asymptotic giant branch stars. These are more massive stars. There are fewer of them. The ratio is about 4:1. So the AGB stars provide a pedestal, but they don't prevent you from measuring this discontinuity. So essentially what we're doing is measuring the first derivative of the luminosity function, the inflection point, and we've done this in many different ways. We use edge detection techniques. This is the so-called Sobel filter. We've done maximum likelihood techniques, et cetera. When you have good data, many stars and high signal to noise, these agree extremely well. So we have looked at these two different approaches. Here is again showing where the red giant branch lies. Here are the asymptotic giant branch stars, luminosity function of the AGB and the RGB, and we're looking for, again, this inflection point that signals the discontinuity. So sometimes, I appreciate an audience looking at these color magnitude diagrams, looks like a bunch of dots. These are all individual stars within individual galaxies that we're looking at. But the technique is very robust and repeatable. And just to emphasize again, we don't need to know what the slopes of the AGB and the RGB are. And just to use a simple analogy, if you're walking along this cliff, it's when you reach that discontinuity, you know it, and it doesn't matter what the slope is as you approach the discontinuity. So it's very well determined. Here are some of our JWST data, and for galaxies now here from 7 megaparsecs, 15 megaparsecs here, and 22. And in our first cycle proposal, we limited ourselves deliberately to galaxies with distances less than about 22 or 23 megaparsecs, because we didn't want to have, if crowding effects were going to continue to be important, we wanted to ensure that we got high signal to noise data that we could be certain weren't affected by crowding. And for the TRGB, as I said, in the halo, these stars are very isolated and crowding is not an issue. But you can see, again, just by eye, at 10%, you can probably measure this by eye, that the position of the tip is well delineated. And here's the signal to noise at the tip, and it's very high. It's the Cepheid photometry from HST in some cases has signal to noises of even 1 to 2. So when you're pushing again out to the not even the largest distances, but the lowest period, low luminosity Cepheids, it can be really difficult to achieve high signal to noise, which again makes your photometry challenging. And this is just a overall view of the galaxies in our early sample. And you can see, again, we have measured the tip in all cases. I just want to say, and I noticed an email about 10 minutes before I logged on, which I haven't had time to go and follow the details of the implications of that. But these are archival data that were taken by the SHOES team in this NGC 4258, which is the Maser galaxy. And we have measured a TRGB distance to this. So here is the Sobel filter applied to this data. And we get a very good agreement with the SHOES group, and maybe if you're online, you could say it sounds like they've looked at the 0 point and it's changed slightly. So maybe so I don't know yet because I haven't had a chance. I only got it 10 minutes before. But in any case, the signal is unmistakable, and I think what's really exciting for me is that as we approach the next few years, many of us are going to be looking at the same data, and any disagreements or differences that we have in the analysis, we'll be able to see those directly and understand and get to the bottom of. But point I want to make now is there's actually emerging really good agreement when we're looking at these different techniques and measuring with different groups, which is very exciting. So here's a second method, this so-called J-region asymptotic giant branch method, and this is the newest of them, as I've said. And in this case, you have a degenerate carbon-oxygen core. These are more massive stars. They have masses that are maybe 1.5 to 4 or 5 times the mass of the sun, and they're double shell burning. They have both a helium burning shell and a hydrogen burning shell. And it turns out that in the J band, in this in a very narrow region in color and in luminosity, the scatter in the luminosity of these stars is very small, and therefore makes a very, very promising distance indicator. And astrophysically, the reason that we see this narrow band in luminosity is that for the more massive stars, so as carbon is being brought up to the surface, so-called dredge-up process, for the hotter stars, the carbon is being burnt before it actually burns into nitrogen before it reaches the surface. And what is causing these stars to be red is the dredge up of the carbon into their atmospheres. For the lower mass stars, the dredge up is not efficient and the carbon never reaches the surface. So astrophysically, there's a reason that you would predict these stars would have a very narrow dispersion in luminosity. So this is something that was first noticed by Nikolaev and Weinberg. They actually measured the geometric tilt of the Large Magellanic Cloud about 25 years ago, but the method didn't go anywhere. Nobody picked up on it. And until Barry and I began to look at this in the context of extragalactic distances and to examine data that had already been published and was available in the literature in the near infrared. And you can measure the luminosity function of this distribution of stars. It's nearly Gaussian. And you measure the mean or median and mode, and we've looked at all of those. And you can compare those with the distances that you obtain for tip of the red giant branch. And this is work that we did a few years ago now that suggested to us this was going to be a really interesting new method for measuring extragalactic distances. And
Can I interrupt? I don't know if we can ask questions. I raised my hand.
I would prefer the questions at the end, if possible.
Okay, thank you. Sorry.
Okay, let me continue and happy to answer questions at the end. So this is now one of our JWST frames. This is F115W as a function of the color again in the JWST bands. And you can see this distribution of stars in the J band in this narrow range in color and its luminosity function. And these are the fields, again, that we have observed, the same galaxies that I've been discussing. And the measurements are being made outside of these white circles or ellipses. And the point, again, being stay away from the disk where you have ongoing star formation, where we see asymmetric luminosity functions, where you have to correct then for presence of more dust and star formation and crowding. So the idea is to limit the measurements to the outer regions, outer part of the disk of these galaxies where the luminosity functions appear to be well behaved. And so I think at the current time, one of the uncertainties that we have to address is where do we best measure this luminosity function for these stars. And what Abby Lee has done, doing her thesis at University of Chicago, is to measure the position of this mode as a function of the radial distance from the center of the galaxy. And you can see it shown here in all cases. And you see that it's higher in the inner parts. That potentially is from crowding. These stars are more crowded in the inner parts. And then measure the derivative of this distribution to see where it crosses zero and to see where this levels off, and where we can make a measurement that reproduces at a variety of radial distances. And so it's quantifiable. It can be, again, checked by others. Okay, so that is the JAGB method to date. And let me just say a little bit about Cepheids. Again, well known probably by most people in the audience, but these make excellent standard candles. Again, if you can standardize them in use for a century and with high quality data, they give really accurate distances. Now, as I mentioned, the amplitudes of these stars decrease as you go to longer and longer wavelengths. So this is just showing the so-called light curve of a Cepheid in the ultraviolet through to the near infrared here, K at 2.2 microns. And you can see that the amplitudes are decreasing. And the same is true for the dispersion in the PL relation. This is what we were able to show in the 1980s when CCDs first became available, that as you go to longer and longer wavelengths, again, this temperature sensitivity decreases in the infrared and you get lower scatter and clearly an advantage when you're measuring distances, as well as lower sensitivity to dust. And so once again, if you have multi-wavelength data, and what we found is even with 2 filters and using a method developed first by Barry Medora using a quantity called W, which is essentially takes out the reddening component, you can correct for the dust or get a reddening corrected magnitude. So why is 1% so hard? And that requires just a slight digression. Let me just say a little bit of the work that's gone into the measurement of these distances and luminosities of these objects that we're using. We used a new updated pipeline from Space Telescope, reanalyzed the archival data, as I said, started from scratch from the raw photometry. We didn't include the H-band data just because of the more severe crowding effects with HST. And the artificial star experiments that we've done 1,000 stars for each Cepheid. So we put in stars with known colors and magnitudes, and then around the Cepheids, we extract those in the same way as we would measure each individual Cepheid. Now, of course, we don't know what the crowding is for a given Cepheid. It's a statistical correction only. And there are different ways that you can approach this. So there's uncertainty involved in the corrections themselves, but at least you get some sense of how crowded an individual Cepheid might be. We can then put together extinction plots. We use 2 independent methods for point spread fitting for an internal check, also compared with aperture photometry from Space Telescope, another external check. As I said, we did as much as we could initially in a blind fashion. We've looked at 2 supernova samples for which there is good agreement. And the calibrating galaxy is NGC 4258. So that is currently one of the largest uncertainties. We have a single calibrator only. That distance has been estimated to have an uncertainty of 1.5%, but it's a single object, and there aren't other galaxies that are close enough that have masers and a favorably inclined disk to do to measure the Keplerian rotation and to measure a geometric distance. NGC 4258 is a distance of about 7.5 megaparsecs, and the next closest galaxy is 50 megaparsecs. So we wish nature would deliver us more nearby objects where you could make these kind of 1.5% measurements, but that's what we have. And I should say that the objects that we're looking at, the TRGB and JAGB stars and in these galaxies are too bright in the Milky Way and the Large Magellanic Cloud for us to observe with JWST now. So that will require a second step of transforming to other systems and adding in those calibrators, which will have its own set of uncertainties. But right now, everything is on the same system. So in a sense of the relative calibration and seeing how the relative distances given that calibration agree or not is important. Okay, just very briefly say, as we went to the infrared, what became really apparent is that if you have really good phase coverage, really good colors, if you look at the period luminosity relations, these are stars in the Large Magellanic Cloud, data from Las Campanas in Chile, and also Spitzer at 3.6 and 4.5 microns. But what I wanted you to notice is the one extremely small scatter in this relationship, so essentially the intrinsic scatter of Cepheids at these wavelengths, but also how the residuals, the scatter away from the fit agrees for this sample, even though, again, very differently calibrated. these are very different telescopes, et cetera. But when you have high signal noise data and these light curves are very well determined, we knew what the periods were so that we could schedule the observations at Spitzer to really fill in any gaps in the coverage. So again, extremely good indicator if you can standardize them. The challenges, of course, increase as the distances increase. We still need optical data for the extinction corrections, and the farther out you go, your precision and your accuracy will decrease. So here are some examples of, this is NGC 5643 and 4639. Some of the galaxies in the SHOES sample have many, many Cepheids. The PL relations are well populated, some not so much so, they're more challenging. But again, you can see that the scatter decreases as you go to longer wavelengths. I just want to make the comment that we often talk about a Cepheid period luminosity relation, but it's important to keep in mind that it is a Cepheid period luminosity color. There's an intrinsic color that is adding real scatter. It's a physical, it's not noise, scatter to the period luminosity relation. We don't know the intrinsic coefficient, what the color term is. We also have to correct for dust, which affects the color. And there's a metallicity term. And we can't measure the metallicity directly. As I said, we do this by proxy with H2 region abundances, but all of those have to be well determined. 0 point. Just briefly, there's still debate in the literature as to what the metallicity coefficient is. In the calibrating sample, not for us right now because we can't use the LMC, but the LMC and 4258 and the Milky Way have different metallicities. So even at the level of the calibration, you do have to worry about the metallicity. And the fortunate thing is right now that our sample of target galaxies from JWST in the mean has a metallicity that's very similar to NGC 4258. So at the moment, that's not a significant source of uncertainty. We need to do these artificial star corrections, as I said, and different groups are getting different results for the artificial star corrections. That's something I think we're going to need to understand. They are smaller with JWST, and I haven't shown the H-band ones here. They're quite large. And I think the important thing to say again about these artificial star corrections is, they depend on wavelength. If you get them wrong, you have different stars that are contributing to the crowding effects at different wavelengths. You get them wrong, you get your colors wrong, you get your reddening corrections wrong, you get your metallicity corrections wrong. So crowding will never be the sole source of uncertainty, but these effects are covariant. And so they could have potentially a larger effect than I think right now we're taking into account. So here is a comparison of our JGB distances with those measured with the tip of the red giant branch from our new JWST data. And you can see that the agreement really is excellent. The scatter is small, the offset and 0 point is small. These are the scatter is at a level of 1 point something %, and the offset is again better than the 2% level. So these are stars that don't know anything about each other, different stages of stellar evolution, different parts of the galaxy, different methods used to measure their distances. So it's I think an indication that we're getting a lot of progress in measuring the distances to nearby galaxies. It wasn't that long ago that a plot like this had factors of 2 different in the 1980s still. And here is showing also data from the ground. These are data from work that Abby Lee led, measuring JGB and TRGB distances using the 4-star camera at Las Campanas. And then these are the new JWST distances. So over a very large range in distance, it's about a factor of 50, the technique really does, both techniques seem to hold up. And I think with any new technique, you worry that there may be unknown systematics. Again, we don't know, is there some star formation effect? Is there something yet that we don't understand in these stars? But in comparing the distances this way, if there are systematics, we're seeing that in the scatter, which is very small. So the systematics don't seem to be dominating in a way that we can see. Now we're comparing our Cepheid distances with those of shoes. That again, these agree well. There is some scatter. And I think what I would say at this point is the shoes team does have more extensive data on NGC 4258 than we do with our cycle 1 data available. That will improve in future. But again, the agreement, I would say, is very, very good. Now, just to emphasize the difference, so that what Shoes has used is 4 calibrators now for the nearby anchors. And at the present time, we have NGC 4258. And what we do have are these 3 rungs here, which Shoes is now beginning to measure TRGB and JAGB distances also. So that is, I think, very welcome that we're going to have a lot of different ways of coming at this and understanding what possible systematics can be in either the methods or the way of analyzing the data, and then tying into the type 1a supernovae. So step A and B, the 3 rungs right now of the distance ladder. And the largest systematic, particularly for the JAGB and TRGB distances, is this distance to the anchor, 1.5%. Tying into the type 1a supernovae, let me say just a few words about the Carnegie Supernova Project data, which is the primary sample that we have looked at. And this is a program, Mark Phillips and I were co-PIs for this program at Las Campanas, took place over many years. It's a survey, not a survey program, it's a follow-up program. So other people found this supernovae, but what we could do was follow these up with very high cadence and with many wavelengths, and also to get spectroscopy at different phases so that we could do the K corrections very accurately. We were very careful about the calibration. We measured fluxes using instrumentation that checked on whether we had a drift in the calibration over the many years of the survey, and made sure that that was not occurring. So in terms of systematics, again, this is well sampled. It is a consistent data set. There are now spectrophotometric observations of many of the Carnegie Supernova Program supernovae, and it is checking out extremely well. The 0 point seems to be very stable, and you can use other surveys and put them together. And Shoes has done an incredible analysis of 18 different surveys and put those all together. But I think this has merits also, and as I said, the spectrophotometry is indicating that the 0 points for these data are very accurate. So this is one version of the Hubble diagram for the CSP sample. And here, the middle panel here is just showing the scatter around the Hubble diagram nearby, so that there are many supernovae here that have been discovered at low redshifts. Those tend to increase the average peculiar velocity to a value which is high compared to what is measured with the rest of the sample. Dylan Brout did a really nice job with their large sample, showing that if you exclude the supernovae less than redshifts of 0.01, then you really don't have to correct for peculiar velocity effects. Here's just one example of the MC analysis that we did with PYMC, and an earlier version of this, we solved for the peculiar velocity, but that just gave very funny contours. It's well determined. Again, Brout finds a value of 240. Many groups find this average peculiar motion to be about 240. So we just simply assume that now has almost 0 impact on the ultimate determination of the Hubble constant. One thing that did have an impact was and this, I thank the Shoes group for pointing out that the initial version did not take into account the fact that we were getting a small dispersion in the calibrators relative to the more distant sample, the scatter and the supernova magnitude. So we added an additional parameter to account for that, and that increases the uncertainty in the Hubble constant. And so if we combine then the results that we get for the different methods, at the current time, we're getting a value of just shy of 70 with the statistical uncertainty shown here and systematic uncertainty shown here. And we do prefer to keep those separate, just because I think it's clear where progress can be made in future to try and bring down the uncertainties and the different parameters that are contributing at the present time. I think one concern still that we need to put to rest is whether or not the more distant sample is free of crowding effects. And this may be a place where we might have slight differences with shoes. And I should emphasize, we're agreeing really well with shoes. I think that's one of the really new and interesting and important results to come out of all of this. And what makes me think in the next couple of years, we're going to get to the bottom of the remaining uncertainties and we're very likely to converge, I would say very soon. What I think is a little bit something that we have to understand still, the nearby calibrators. So these are the galaxies that have type 1a supernovae and Cepheid distances. And here is the peak luminosity, peak magnitude of the supernova as a function of distance of the supernova. And there is a slight trend in the sense that the nearby galaxies, the ones with the lowest error, so if we divide the sample by those that have the smallest errors, the best determined distances, and probably best observed supernovae, they have a brighter absolute magnitude. And it's subtle, but it's not negligible. And you could say, well, these have been well determined with HST, and there's been a study that shows that crowding is not important at an 8 sigma level. But I think my personal view is there's more work to be done and will be done with JWST to confirm that that is the case. So if we look at these are distances measured by the Shoes group in 2016 and in 2022. So just the distances given in the tables in their respective papers. And you can see that this is reanalysis now of the same data, same galaxies, that there's a systematic offset in the mean. It's about a 1.5%, just over 1.5% difference, which is again small, but it's systematic. And in a couple cases, it's even 15% in distance, 0.3 of a magnitude. So these distances are hard, and they're hard. I'll leave it at that. So we're going now. We're looking at galaxies here at about 20 megaparsecs. The original sample, the 2016 sample, didn't go as far as the whole sample now goes, and so we'll see. So one of the galaxies is at 80 megaparsecs. That's a challenge. And just to emphasize that, so the galaxies so far that have been measured with JWST and HST are shown here for the Reese 2016 sample. So the galaxies that our CCHP group have looked at are these red triangles. All these measurements are Shoes measurements. These are the differences between their analysis in 2016 and 2022. And so 2 of the 5 galaxies that have been used to test whether crowding effects are important or not are the 2 that didn't have much of a difference. They're easier to measure. There are lots of Cepheids. The crowding doesn't appear to be that strong. And so again, there's one galaxy now at about 40 megaparsecs, but it remains for these most distant ones to be looked at in more detail. And we'll, it's a simple question: are they free from crowding effects or not? Have crowding effects been ruled out at 8 sigma? I think that's an empirical question, and we'll shortly learn the answer to that. We ran through a number of tests, different ways of computing the Hubble constant with different redshift cuts and different with metallicity, without metallicity cuts, looking at different wavelengths from the CSP, comparing the absolute, or using the supernovae from the Pantheon survey, and so on. They agree remarkably well to within a sigma, which is good. They appear to be robust. But again, we need to be concerned about whether or not there's a systematic effect in the peak brightnesses of this nearer sample, and whether it's a purely statistical effect or whether there's also systematics. And I think at this time, we simply don't know the answer to that. So here are 3 methods. The green are the JGB, and the red are the TRGB, and these are our Cepheid results. Our uncertainties are larger at the moment. We don't have as large a sample for Cepheids as the Shoes group does. and we only have the one calibrator, as I said. The width of the Gaussians here represent the statistical uncertainties, and we have deliberately been very conservative in the uncertainties that we've adopted. And these bars here indicate the systematics. The gray line is the cumulative distribution, just a frequentist estimate of the Hubble constant, and the black is a Bayesian analysis shown here with the uncertainties, both statistical and systematic shown here. So I think the statement to be made, and it's a double statement, these results are consistent both with Lambda CDM and with SHOES. We don't have yet the statistical power to discriminate one way or the other. One can say, you don't need new physics. That's a perfectly valid statement, but it's also the case that it could be consistent with there being attention. So I think the next few years are going to be very interesting. JWST is really ushering in a new era in terms of the overall potential for decreasing the uncertainties in the measurements of these nearby galaxies. The fact that there are different groups, that there are different methods, and more galaxies to come is very encouraging to me. The TRGB and JAGB distances are actually agreeing at the percent level, which is phenomenal. That sentence couldn't have been constructed for any distance indicator until very, very recently. And all three distances are agreeing at they're at better than a few percent level. So I think in the next few years, as we get more JWST data going out to these more distant galaxies in the SHOES sample, that we can reassure ourselves one way or another that either crowding is ruled out at 8 sigma or maybe not yet. And is there a systematic effect? These are questions that will have answers, I believe, very soon. So let me just end by saying that at the moment, we're getting a value of about 70, and I look forward to the next few years. So let me stop there. Thanks very much.
Thank you so much. Thank you so much for the very nice talk. Dillon?
Oh, yeah. Hi. Thanks, Wendy, for this. Coming from the supernova perspective, I'm trying to understand, actually, maybe if you could go back to the slide with it's just the basic posteriors, the three posteriors, and then the gray and the black combined. From the supernova perspective, I was excited to see this result and the consistency between the supernovae. I was surprised to see how small the error bar ultimately was, with roughly 10 or sometimes 9 or 8 or 7 supernovae in the second rung. And I'm trying to understand how you actually combined these, given that they share supernovae. So you mentioned there's the frequentist curve there, which, if I understand, it's basically summing those curves. And then the Bayesian product, how do you do that and deal with the supernova?
Yeah, so the supernovae effectively are going into the estimate of the statistical uncertainty. So that is what is governing our statistical uncertainty. The systematic is, and that's coming out of the MC analysis, MC analysis. And the systematic uncertainties have the distance to NGC 4258, and that is for the JAGB and the TRGB, the major systematic. And then things like the calibration and what we do relative to NGC 4258 in terms of period cuts for the Cepheids.
So this, sorry, I didn't mean to interrupt you. The systematic that you're showing here is not shown in the curves. It's a separate number that's assessed separately.
Separate.
And that's so right. Okay. And so on the statistical side, sorry, you were saying, how do you get the statistical side?
So the statistical is what we determine from the MC analysis. So allowing for those 8 parameters and fit to that, and the uncertainty that we get is what we take as the statistical uncertainty for the type 1As.
Okay. Yeah, I guess. And I see messages flying by in the chat, but I'm not sure how you can, given that there's an intrinsic scatter in the supernovae of, as Mikhail said, somewhere in the paper, it says 0.19 mag, that should be a floor, as far as I understand, in the uncertainty that no matter how many second rung calibrators, Cepheids, TRGB, JWST, you add, you can't get lower uncertainty because you're limited by the supernovae. I guess I'm still not wrapping my head around that.
Yeah, well, let's have a discussion, a further discussion about this after. It's something Chris Burns and I have gone around and round and round on, and so it's something.
Okay.
Let's discuss
sure.
that further.
Happy
to do so.
Okay, thanks.
Thank you. Adam?
Hi, Wendy. Very nice talk. I enjoyed it. Actually, while you're on this slide, I'll just follow up. So I think I agree that there might be an issue here. I think the green, red, and blue curve are the three different methods, but they all use the same 10 supernovae. And so I think taking the product of the three is turning that into 30 supernovae, and that might be something you want to look at. But my question is actually about that correlation you showed with supernova magnitude and Cepheid. Can you put that up? I think it was a couple slides ago.
Supernova magnitude.
That one, yeah. So on the upper plot, the x-axis there is the Cepheid distance.
Yeah, that's correct.
Okay.
Yes.
And the y-axis is the absolute magnitude of the supernova. Yeah.
Yes.
But the absolute magnitude of the supernova comes from the apparent magnitude of the supernova minus the Cepheid distance.
Yes.
So the Cepheid distance shows up on both the x and y axis here. And so I think that is what is producing a little correlation, is that they're not independent axes.
So that, that's looking at the correlation. If we just look at the sample itself, I mean, if I divide by just uncertainty, right, calculate the absolute magnitudes of, the nearby well-observed, well-determined distance sample with low errors and compare that to the other half of the sample, there's a difference. So, if I agree with you
but
on
I think I'm saying something different. Is I'm saying that you can't measure the absolute magnitude of the supernovae without the Cepheid distances. So I think you have to keep independent the Cepheid distance. And I think you want to look at not the absolute magnitude of the supernova, but the apparent magnitude, because that's going to be independent of the Cepheid distance. So I just think you're independent.
Yeah, but I
I
get your point, but I think that, what we need to worry about still is, are those distances that, where the supernovae been measured at galaxies at greater distances, is there an issue with the distances? So, I take your point in the plot, but I think we need to understand how well.
I'm just talking about this plot. I'm just saying I don't think this plot, I think you have to deal with the correlation of the two axes.
I think it's a fair point, but my point is that the nearby ones with small errors have a different mean than the distant ones, and it is the distance that I'm concerned about. So if there still is a crowding effect, and I think we disagree on the potential importance of that, it's the distances where I think it's likely to be the cause. So yeah, I hear you, but I think it's the distances really that are important. And we'll see, that's coming. We're getting data that will allow us to determine that in the next few years.
Yeah.
Okay, thank you. Scott?
Hi, thank you for a great talk. My question, I'm now generalized because it's dated. But my question is how important the physics of the star core was important for these measurements, like QCD, that physics. It was on that one slide, but sorry to interrupt also.
Sorry, I'm not understanding your question yet. The star core. So, are you talking about?
We're talking about the helium and the hydrogen process.
Yeah.
We don't understand that, right?
We do understand that. We understand that well. It's been well modeled, and people like Lars Bilston now in his group have modeled this, and others for decades. It's very well understood, but I'm still not sure if that's answering your question.
Well, I guess I didn't know that. And are you sure? And I'm not trying to be aggressive, but I thought this was
I think in terms of the astrophysics, these are, Lars Bilston working in this field.
Oh,
You know,
sure. Yeah.
he's
But
the
I thought
expert in this.
was tough.
And what's that?
I thought this was a tough problem. I'm not trying. I thought this was a tough problem. So
Okay,
you're telling me not
but
this.
the point I also should make in addition to this is none of these distance indicators is being used from the physics of the objects. These are all empirical correlations. What we're doing is observing them, and we're using their properties to measure their distances. And whether we understand them theoretically or not, and clearly, the bombs that are supernovae, how well do we understand those? We don't predict those luminosities well from first principles, nor the Cepheids. But of the various methods, I would say, and I know Lars would agree, that the TRGB is the best understood physically. But to emphasize, we don't use the physics. We use an empirical measurement. That's how
you answered the question I should have asked. Very good. Thank you.
Thank you. Marina?
Yes, thank you. It's great to see these results. Thank you so much for giving the talk, particularly after you have previewed them at the Royal Society. And from the theorist side, Andrew Little and I have written an article saying that, if this is to be new physics, we really require exquisite data validation. So a big thanks to you and the community for keeping to pursue the source of could it be systematics or not, because it is of great value to the community as well at all. So a big thank you and congratulations on the presentation.
Well, thanks for the words. I do feel strongly that extraordinary claims require extraordinary evidence, and I think the data are getting better and better and better, and we're getting there. I mean, and I think it's human nature to want to be there and be done, but I think there are still things that we need to be thinking about. And what I feel very optimistic about is James Webb is really offering us a tool that can get us there in short order. But the other thing to be said is that independent of the local distance scale, you want things like, I would say you want gravitational wave, neutron star binaries, and things that are based, again, on completely different physics that have nothing to do with the calibration of local distance scale. And do we understand dust and the absolute calibration of dust well enough to, things that will affect all of us. And if you're going to make a measurement at the 1% level, you need several measurements at the 1% level to rule out systematics. And we're just getting, each time we improve the technology and are able to make more accurate measurements, that's where we learn about the new set of systematics that we probably couldn't even address with the previous set of data. So, as I said, this is a status report, and we'll see where it goes.
Thanks so much.
Thank you. George?
Yeah, so
I'm not hearing George. I don't know if
He disappeared. Yeah, I think so. So let's go ahead. Philip?
yes, can you hear me?
yes.
Yes. So with regard to the Hubble tension, two of the easiest explanations are that the local redshifts are too large, or that which could be the case if we live in a locally underdense region, or that the absolute brightness of Cepheid supernova and so on have been overestimated. And as you mentioned in the answer to the previous question, these things are calibrated. They're not calibrated. They're not calculated from stellar models and so on. But in principle, one could do that. Presumably, it's not done because the uncertainty is too large. But I'm just wondering, how large is that uncertainty? Is it a factor of 2, or is it at the percent level, or how accurate can we actually predict the brightness of the Cepheid with a given period from first principles?
So, I mean, you can do it. Of course, the Cepheids don't go out far enough to measure the Hubble constant without there still being a lot of noise from peculiar velocities, right? So you can do this, but what you have to remember is that these stars are pulsating stars. They're supergiants. Their atmospheres are pulsating. So you can do a calculation of the core luminosity and understand how fusion is taking place in the core and how the star is evolving. And then you have this overlying atmosphere that is, you know, going in and out. It's sometimes shocking, and at different wavelengths, you have scattering of radiation in the atmosphere by different chemical elements. And so there are a lot of steps that you have to go through to say, okay, this will be the final luminosity and color of the Cepheid. And those uncertainties are large enough that, you know, what you would want to get from that is going to be dominated by those kinds of uncertainties. It's a very difficult problem. These are dynamic atmospheres, and, you know, you need three-dimensional models, and you need, you know, to understand the opacity as well, and various things that are not well enough constrained to give you at this point is nearly an accurate luminosity is what you can do by empirically measuring these things. I think
Right, that's why they're not used.
observations are going to inform. Yeah, the observations are informing the theory.
Right, that's why they're not used, because they're not competitive. I'm just wondering, is it wrong by, you know, is it uncertainty of a factor of a few or 10% or?
You
how
know,
bad
different
is it?
people will have different estimates of how well you can do this. And you know, I think what's interesting too is there aren't large numbers of groups who are working on models of Cepheids. There are many more who are trying to explain the Hubble tension. And I think, you know, the field could use more smart people to model Cepheids, because, you know, ultimately it would be good to understand them at a high level of accuracy.
Thank you.
Thank you. George is back. So, George.
Adam cut you off. Who cut you off?
George, we can hear you. No.
I think George was going to say that the Hubble constant is above 70 from Planck.
Okay, but he's not talking.
And
So
we missed it.
He put it in the chat and then he disappeared. I don't know.
no, he has a problem. So let's go ahead and let's see.
George says he has a problem.
Yeah. Sean?
Hi, thank you. Thank you for the very nice talk. Could you go back to your slide with the JHB color magnitude diagrams?
Can you hear me now?
Yes, you're back.
Okay.
Good.
Yeah,
Okay,
yeah,
I'll
go
stay
ahead.
quiet and then maybe I'll.
Which one, John? This one or
Okay,
the
should I go on? Yes, thanks. Can you explain or clarify why some of the J regions appear flat with color in some of the diagrams and some of them appear tilted?
I mean, in terms of the color magnitude diagrams themselves, that actually is an optical illusion. I've looked at this too.
Have
And
you
it's
measured the tilts for these J regions?
Abby
or the
has.
slope?
I can't give you a quantitative estimate right now, but it's interesting. You know, depending on how you plot this, you know, when I first looked at them, I thought, oh my goodness, there is a tilt, but there isn't. It actually is quite mild.
Where does that illusion come from?
It's partly because if you look at these extreme carbon stars, it seems to follow a trend. And those we know are decreasing in luminosity with color. So yeah, I agree with you. By eye, it looks like it. But if you look at this without the shading and without these other stars, and Abby has quantitatively measured it, there's not a big tilt.
Okay, and so what are the slopes? Or what's the measurement of the tilts? Is it consistent?
Yeah, that's what I can't give you numbers offhand. We'd have to get Abby here.
Is that in the paper?
I don't believe it is in her paper. But yeah, that would, you know, that could be quantified.
Okay, thank you.
Thank you. So, George?
Yes, okay. So we found an error in the Planck analysis and H0 comes out to be 73. So
Oh, so Adam was wrong. He just told us that you put in the chat that it was 70 and then you disappeared.
No,
No,
I
no,
said
no,
greater than 70, but anyway, go ahead.
Okay. So no. So this is in regarding the combined the combined posteriors to come up with the black line. I mean, if you want to combine them, you know, take into account the fact that you know, you're using the same supernovae. I think you have to make a model for the potential systematics. So what you could do is you could do an MCMCM analysis and just, with the assumption that there's a constant offset between the JAGB and the tip of the red giant branch, and an offset to the the Cepheids, and then see what your combined thing is and what you get for the offsets. And I think that if you do that, what you'll find is a statistically significant offset of the Cepheids relative to the other two distance indicators. So I think that would be
okay. That's a good suggestion.
I think that'd be quite a nice thing to do. I mean, of course, really what you should do at this stage is just stick with the with the distances, the distance moduli.
Yeah, that's my feeling. And the rest is going to improve, but where we're really, I think, needing to understand where are any differences is.
But if you wanted to get something like the black line that was statistically a bit more rigorous, then you could do it like that.
Yep, would be another way to do it. Good.
Thank you. Sayantan?
Yeah, so thank you very much for this talk. I'll just have a very quick question. So I am actually from theoretical background. So I am asking that in the red giant branch, I mean, it is a very good candle as you have suggested, but I am asking that like, for example, type 1A supernova or Cepheid or say millipulsars, we have exact theoretical understanding of that. But even if we take the red giant as a very good, say, black box, which gives us a good result, I'm just wondering that what are the physics which would be important in further somebody wants to do? I mean, should one focus on the nuclear physics more for the CNO cycle or helium, or is it the, say, Tolman, Oppenheimer, Volkov, or some relativistic hydrodynamical system one has to simulate little better? So if you can just comment on that, like if somebody wants to theoretically get a grasp on the red giant branching, like how should one parameterize? Should it be like the fluid mechanics point of view, relativistic point of view, or the nuclear physics point of view? I mean, just I was wondering. Thank you very much, ma'am.
Yeah, I think as the models have been improving again, so these uncertainties come down, and then you see where the tall poles are, and so at the current time, different groups have different sense of where those tall poles are, and it's important again to have different groups who are doing these kinds of analysis to understand where the differences lie. But interestingly, they agree pretty well. So at least at the moment, there don't seem to be large uncertainties or parts of the evolution of through the giant branch to the core helium flash that are not well understood. So I wouldn't at this point give you an answer off the top of my head, except to say that different groups are doing this, and the agreement is one of the things that I think gives people confidence that the models are well understood.
Yeah, thank you, ma'am, very much.
Thank you. There is a lot of discussion in the chat about this figure. I don't know if I think we
I'm
discussed.
not in the chat at the moment. Sorry. Let's try and grab glasses.
I don't know if there is someone who wants to comment. I don't know. Dom or
Yeah, I can speak up. Sorry. Thanks, Wendy, for the nice talk, as others have said. I'll summarize my question here in the chat, which has started a little bit of conversation, which is about this plot here. The black curve, I think, as Adam pointed out, I think it makes sense. The statistical procedure you're using to produce the black curve here, it may have some faulty underlying assumptions about independence of the three curves used in that product, but it's otherwise, I think, statistically sound, as procedurally. And you can understand how to correct it for the whatever covariance may be present between these three measurements. But the gray curve, the sum of PDFs, is not a statistical procedure I'm at all familiar with. What is that meant to capture, and how do you sort of justify summing probability distributions, which are typically things you multiply?
Somebody's saying something, sorry. Oh, sorry, I thought I heard somebody jumping in. It's simply, a very simplistic cumulative sum of the distributions, and it's just meant for comparison. And the fact is, it's essentially, we're assuming a uniform prior for the the Bayesian, not favoring one method over another, and this is simply doing the same in a cumulative fashion. So yeah.
I would like, if I could just clarify what I was saying about the black curve. Looking at the analysis in your table 3, it looks like, and tell me if this is right, you did an MCMC run for the whole distance ladder, just doing, let's say, JAGB, and then you did a whole distance ladder MCMC run for just doing TRGB, and then just doing Cepheids. And
Yes.
each of those, you report an error at the end of table 3, and those go into your error, your random error in table 5. And then in table 5, you combine the 3 of those as though they were independent, and that gave you a smaller error. But in each of those MCMC runs, it was the same set of supernovae. It was the same ones in the Hubble flow and the same 10 calibrators. And my understanding is that the error from the 10 calibrators is what is setting the width of the green, red, or blue curve, because it's the dominant error. So I don't think you can multiply those 3 things. I actually don't suspect that they will get narrower at all. I think you have to do a simultaneous fit with the 3 methods and the 1 set of supernovae.
Yeah, so on the to-do list is the simultaneous fit, and I agree with that. And will be done. Yep.
Thanks.
Okay. Thank you. Any other comments or questions? No, so I think we can thank Wendy again. Thank you so much.
Thank you. Thank
you.
So bye everyone. See you next week. There will be Adam talks next week.
And
Bye-bye.
thank you, Jean, for your suggestion too. Good one.
Thank you. Bye.